everyone to another video of 3 minutes with Nathaniel. Today we'll be solving question 1C of MIT Oxford 2015. You are given these 4 functions and we need to find if each of them is true. How do we solve this? The first is using the addition formula, the first method, but we won't do that here as I'm prone to carelessness and I may get the addition formula wrong because often I can multiply sine by cosine, which is very unwieldy, so instead we use something called phase counts. And what is phase count exactly? So we'll define phase count of 4 main functions. 0, 1, 2, 3. And we'll also define switches. Plus pi over 2, minus 3 pi over 2, and plus pi and minus pi are the same, and minus pi over 2, and plus 3 pi over 2 are the exact same. So let us work this out. Sine x plus pi over 2 equals, as it turns out, it is cos x, so plus 1, plus 2, plus 3. Apparently simple definition, but if you put sine minus x, so ps minus x for the negatives, cos minus x and minus cos x are the same, sine x becomes minus sine x and minus sine x becomes this. Now what is sine pi over 2 plus x? Sine pi over 2 plus x, so we count the phase count on both functions. Let's start with this one. So we had 0 plus 1 equals to phase count 1 equals to cos x. However, cos minus x is the same as cos x. So what we do is that we put 1 plus 1 equals to 2 equals to minus sine x. So this statement, which is statement 1, is wrong. Statement 2 asks for this. We can reduce it to a quadratic in sine x by using the identity sine square x plus cos square x equals to 1. 2 plus 2 sine x minus 1 plus sine square x greater than or equal to 0. Sine x plus 2 sine x plus 1 greater than 0. Now if we draw, instead of using sine x, we make x, we, however, get something like this, which is always positive. So this statement's right. Statement 3 asks for this. Again, we'll be using phase counts. Sine x has a phase count of 0 and x plus 3 over 2 equals to 3. Cos pi minus x, so 1 plus 2 equals to 3. So both of these functions equal to minus sine x. You can prove that using addition formula if you want, so this statement is a big tick. Now sine x cos x, how do we do this? We use the identity that 2 sine x cos x equals to sine 2x, which leads to the big trigonometry joke. In binomial expansion, but how? You can prove this on your own, but for now, we'll use this identity. Half sine 2x less than or equal to 1/4. But look, it's half and sine x reaches a maximum value of 1 and sine 2x is exactly the same. So, a big cross for that. So with that in mind, statement 1 is wrong, statement 2 is right, statement 3 is right, but statement 4, which I'll label here, is wrong. So statements 2 and 3 are right. There you go. Different trigonometric statements and a way to prove some phase counts. See you, bye!